The last model that we will talk about in certain depths would be so-called interface-controlled shrinking core model. So instead of the reaction being diffusion controlled, in this case, it's interface controlled. The rearrangement of the atoms from the matrix or host phase to the new phase now becomes the rate limiting step, while the diffusion would be relatively fast. For example, for interstitial diffusion. For interface-controlled shrinking core reaction, it happens typically for decomposition of solids that release with gas. And the assumptions are, for simplicity, if it's 3D spherical shape and shrinking core geometry, which is what we illustrated here. In the center, white portion is for untransformed volume, while the spherical shell represents the transformed volume, and the initial radius is R0, and the current radius for the untransformed would be R, okay? And assume, for simplicity, assume constant rate of growth for the product layer, which means the thickness for the product shell derivative with respect to time, dx over dt would be a constant, okay? Or the radius for the current remaining product would be R0, the initial radius, minus a constant times t. It just tells us it's a linear growth of the product shell thickness. With that, the volume of the unreacted portion would be VR, R for radius R would be 4 over 3 pi R to the power of 3, or pi R cube, okay? The fraction of transformation or conversion would be similarly given by F for fraction of conversion would be initial volume V0 minus the unreacted or untransformed volume divided by V0, okay? So this gives us the fraction of conversion. And then consider the V0 similar to what we derived before in spherical geometry would be 4 over 3 pi R0 to the power 3. Again, R0 would be the initial radius for the phase, okay, in spherical geometry. In this case, the fraction of conversion would be 4 over 3 pi R0 minus 4 over 3 pi R square divided by in the denominator 4 over 3 pi R0 to the power of 3. Okay. And with that, of course, we can easily cancel out 4 over 3 pi. And as a result, the fraction of conversion would be R0 to the power of 3 minus R cube divided by R0 cube. Okay. So this guy gives us a conversion. And remember the transformed portion radius. The untransformed portion radius R would be R0 minus KT. Okay, then we would have the fraction of conversion would be R0 cube minus R cube divided by R0 cube. And for this R would be R0 minus KT. So we R0 cube divided by R0 cube would be 1 minus R0 minus KT over R0. Both are to the power of 3. Okay? And then we can rearrange the F fraction of conversion would be 1 minus, combine these two would be 1 minus K over R0 T to the power of 3. And if we rearrange, we would have 1 minus F to the power of 3 would be 1 to the power of 1 over 3 would be 1 minus K over R0 T. And of course, we can further rearrange, combine 1 and this 1 minus F to the power of 1/3 together. Okay, and the K over R0 T move towards to the left side, we would have this relationship. Now, similarly, this relates the fraction of conversion and a constant of T, constant times T. And if we define k over 0 as k prime, this is the another form to write the kinetic equation. This is for three-dimensional case. If we are dealing with interface control direction for two-dimensional case, such as the decomposition of a cylindrical shaped particle, then instead of all these to the power of 3, we would have to the power of 2, and the overall reaction would write similarly as 1 minus bracket 1 minus fractional conversion to the power of half equals k over r0t. Okay, so this would be the so-called interface controlled shrinking core model. And in this case, the f is from 0 all the way to 1. Okay, and the t in this case cannot be too long because the left side goes towards infinity, but the right side does not. So it has certain range of application.